the very beginning so you can understand me well. First, thank you very much for the local organized community actually provide this opportunity to give a talk. And also, although I cannot see all the audience, I just thank all of you. So this is actually time difference. Perhaps in your place is evening, in my place is early morning. So my talk will be testing gravitational theory with a broken Lorentz symmetry by gravitational waves and black hole observations. I will divide my talk simply to three actual parts. First, consider Einsteins Theory, then consider some observational tests. So finally, just quickly summarize the result. So Einstein's theory, you will see, is a theory that actually brings Lorentz symmetries. It's actually a vector tensor theory. Normally, we know in general relativity, the gravity is described by actually only the metric g mu nu. But here we introduce a vector field, which is also called a ether field. So actually, like what I said, this is a vector tensor theory. So there is actually the vector field actually is called ether field. This is always time-like. So that's why in this theory you will see because it's always time-like, then we actually this ether field define one preferred direction. So which actually will let the Lorentz symmetry locally. Because of this violation, actually, you will see instead of only one species of graviton spin 2 in Einstein's theory, here we have actually spin 2, spin 0, and spin 1. So we have three different species of gravitons. This actually the action looks actually complicated. The vector field you can see now we instead of there only g mu nu, here we have a formal copying constant we call C1, C2, C3, C4. They are all dimensionless and free parameters. Of course, when those 4 parameters are 0, so the theory reduced to Einstein's general relativity, which I always call GR. So when we actually value the action with respect to the metric and the ether field, vector field, we can get these actual equations. Like what I said, we have actually 3 different modes. So each of them actually move in principle with a different velocities. So CS means the spin 0 mode squares. C with the vector mode speed squares and CT is the tensor mode. So they just defined in terms of the 4 copying constant, C1, C2, C3, C4. There's some combination from C1 to 3, which means equal C1 plus C2, C3, etc. So this is actually the theory. The very remarkable purpose of this theory, like what I just said, although the breaking Lorentz symmetry, but still several consistent, and also consistencies with all observations we did actually so far. So this also it's Cauchy problem is well imposed or well posed. So this actually, as far as I know, there are only few theories possess this property. And also, this actual theory possesses all the gravitational radiation channels, scalar, vector, and tensor, as just mentioned. So this is actually interesting in several aspects. So now I'm going to actually talk about the observational test. First, we needed the theory to be self-consistent, which means this has to free of ghost. Free ghost means the kinetic term. If we make a perturbation, we will have scalar mode, vector mode, tensor mode. The kinetic term of scalar mode and kinetic term of tensor mode, the same kinetic term of vector mode. This coefficient has to be positive, otherwise the theory is sick. So you will see there are 3 actual coefficients we call QS, VT, SVT stands for scalar vector tensor. So they must be actually, all of them are greater than 0. The same thing for the gradient instability. So the velocities of this actually through species has to be squares of the velocity has to be positive. So this is actually second requirement. The third one we know if any of them actually the speed of any of them less than 1, we have a Cherenkov radiation. So we do not want this happen. So we require each of the species actually greater than or at least equal the speed of light. Then we also have actually the Big Bang nuclear synthesis requirement, because in this theory you will see the effective Newtonian constant, which we call G Cosmo, is different from Einstein case, which depends on carbon constant C1, C3, and C2. So this is actually one requirement. Another one is we know the gravitational wave 170817 actually tell us the tidal modes, the speed of actually the tidal modes almost equal the speed of light. So this is a constraint. Also, we require theory has to be consistent with all the solar system observations, because here we have actually the ether field, then there's actually a dragging effect, which actually makes the post-Newtonian constant. Two of them are different from Einstein case. We call alpha 1, alpha 2. So this actually has to be, each of them, alpha 1 has to be less than 10 to minus 4, alpha 2, 10 to minus 7. So this is all the constraints so far we actually observe. So if you put them together, you will find this actually there are 4 constraints. One is the C1 source opposite wall has to be less than 10 to minus 15, and the C14 has to be positive, less than about 10 to minus 5. Then C2 also has to be greater than C14, less than 0.095, which this comes from nuclear synthesis requirement. Same time, C4 has to be less than 0 or equal 0. So this is actually the constraints from all the observations we got so far. Now I'm going to move on to study the black holes and also quasinormal mode. Why we know? Because in the last stage of the Wang binaries, so once they actually merge into a final object, normally this is a black hole, so the gravitational wave emitted in this phase can be superposition of the quasinormal mode. That's why quasinormal mode is important now. Of course, now to study the quasinormal mode, actually we need first to find solutions. So far, all the solutions found are spherical symmetry. But unfortunately, all the solutions found so far actually they have been ruled out by current observations, which means they are outside of the phase after actually we consider all the observations. So what we did actually is we first find spherical solution, then actually make a linear perturbations. So to find a solution, analytical solutions are very challenging. What we do actually to try to find a numerical solution with a spherical symmetry. So we use actually we use this actually Finkelstein coordinates. The reason why we use this is because we need to actually penetrate to the actually measured horizon, which is the event horizon normally we see. So the problem becomes complicated, but this is mathematically. The most important difference is that there are two horizons here in this theory with a spherical symmetry. First is spin 0, because remember we have like a spin 0, spin 1, spin 2. But the spin 1, spin 2 mode will not appear with a spherical symmetry. Only spin 0 appears. Spin zero, the speed of spin zero graviton actually larger than speed of light. So this actually spin zero particles define the horizon, which should be the inner boundary of black hole instead of the major horizon. The major horizon defined by the speed of light. Because the spin zero graviton actually has a velocity which is greater than the speed of light, so spin zero horizon actually define the inner boundary. Now the mathematical challenge is the metric is the singular and the major horizon, which is normally we call event horizon. So we have to actually numerically solve this problem. What we do actually, we use actually shooting measure. First, from spin zero to the measure horizon, then from measure horizon to infinity. So we just then match them together. So once this actually is done, we find various solutions with the spherical symmetry. You can see now the solution has different properties depending on the speed of the spin zero gravitons. So first, for example, first case, CS squared is almost equal 1. Then we go CS squared is equal 1.4 something. So we just go on with the different speeds of spin zero gravitons, so we get actually different solutions. But all those solutions actually satisfy the observational constraints. We get actually many solutions. Then we find we calculate the different actual physical quantities. For example, the so-called the angle what's called the measure horizon RG, and also the mostly internal stable photons. So we will find actually there's no significant difference from actually Einstein's theory, which in certain sense is good, means this actually theory actually survived from observation. Then actually we move on to actually study the linear perturbations of the black hole solution, the Quasinormal mode. So after that, actually we consider other parity perturbation. We know actually the linear perturbation can be actually divided into odd or even parity perturbations. Hello, can you hear me? Hello? Hello?
Hello.
Oh,
Yes.
can you hear me?
Yes,
Oh,
yes.
okay, sorry. Okay, if you have any question, please stop me actually. Otherwise, I can go on. Yeah. So this actually, we just consider other perturbation. Then we find actually, before we calculate the Quasinormal mode, we found that the other perturbation actually is stable. We have to actually set another parameter, which is C4 equals 0. So this actually, in certain sense, surprise. We didn't predict actually this is the case just because of stability. Now actually we are studying the Quasinormal mode. Like what I said, the challenge is because the inner boundary actually is the inner boundary actually inside of the event horizon. So we have to actually put actually from inner boundary to event horizon then to infinity. So we're still working on the Quasinormal mode, but the stability analysis already tells us C4 has to be 0. This work is still going on. We also did some work to study actually the gravitational radiation in the inspiral phase. For example, when we have actually two compact astrophysical objects like a black holes, we consider the gravitational waves. So before we consider actually binary system, actually we first calculated the gravitational wave emitted by many body system using post-Newtonian theory. This already has been done by a couple of people, but we just actually rederive the result, then correct some actually typos. There's some mistakes actually. So in this theory, you can see there are 14 actually independent components, like in Einstein's case, we just decompose this 14 composed into scalar mode, vector mode, and tensor mode. I will not actually go to so details about the technical part. Just say from this actually scalar mode, vector mode, tensor mode, we can construct the gauge invariance. Then you will see actually there are total 10 because of total 14, but we have 4 gauge freedom. So we just actually 14 minus 4, we have 10 independent perturbations. Once we get this actually, we impose certain gauge condition, then we just actually calculate the perturbations. We use phi ij for the tensor mode, psi I, the vector mode, then actually phi 2 actually, this is the scalar mode. So once we get this actually, we get all the modes, then we can consider the effect of this actually gravitational wave when pass through actually the detector. Then this actually will be given by so-called geodesic deviation. So they just actually calculated the geodesic deviation. You can see we project this actual perturbations into totally 6 different modes. So normally we see H cross, H plus, H cross, and HB, HL, HX, HY. I will explain later what it means. So HB actually is called scalar polarization. H also scalar polarization, but along the propagating direction of gravitational wave. HX, HY, so due to the vector modes. Of course, you can see in Einsteins theory, we have only the first 2, H plus, H cross. But in Einstein theory, we have all the 6 modes. So they are all of them are different from 0. The only difference is the 2 scalar modes actually they are not independent. They are actually linearly connected. So that's why we have actually totally 5 independent modes. 2 for spin 2 graviton, 2 for spin 1, and 1 actually for spin 0. So here actually should be 1. 6 modes, but only 5 independent. So after that, we consider the emission of a power spectrum. Actually, you can see this is actually the power actually emitted the power. There's actually 3 terms A, B, C. So A, B, C are functions of the 4 parameter Ci. The A term actually contains all the contributions from the 6 mode, means scalar vector tensor. In Einstein's theory, only A term difference from 0 equal 1 actually. B equals 0, C equals 0. B actually is due to actually the monopole, C actually due to dipole. So of course in monopole, dipole radiation in Einstein's theory is 0, so we have only quadrupole radiation. But in Einstein's theory, all of them are different from 0. So what we do actually, once we have a general perturbation, general actual formula for embodied problem, we apply our formula to actually triple system and binary system. First, actually, we consider the first relativistic triple system, which was observed in 2014. This is still the only one relativistic triple system. We know actually we observe many actual triple systems, but their mass always are smaller. So this actually is the only relativistic triple system we observe so far. So there's actually 3 compact objects. The first one is a neutron star with a mass 1.44 solar mass. The second actual one is 0.2 solar mass, which is a water dwarf. So this actually 2 binaries. They form an inner actual orbit with a period of 1.6. And the third one is also water dwarf, the mass is 0.41, which actually forms the third one, another actually circle, so with a period of about 1 year, 327 days actually. So this actually the 2 planes of the binaries are almost equal. So after that, actually, we use the observational data to calculate the effect, the emissions of due to quadrupole, monopole, and dipole. What we found from this figure, you can see there's several lines. There's A, B, C. A is the blue line, C is the green line, B is the red. You see the B part is very small. The amplitude is 10 to 7, but the blue and green line, they are almost the same. Like what I said, the blue line is A, which represents quadrupole. In Einstein's theory, we have only quadrupole radiation. But in Einstein's theory, the dipole also almost the same amplitude. So this tells us if we have a triple system, then through the observation of dipole and quadrupole, we can actually distinguish Einstein's theory from Einstein's ether. So since in Einstein's theory, actually, there's no dipole radiation. So actually, now we do find a candidate for the triple system, which is the GW 1908-14. So people propose this actually due to triple system evolution. So this is actually our application to the triple system, but we have not observed any gravitational waves from a triple system except this candidates. So now we move on to the actually gravitational wave emitted by binary systems, because we already observed about 90 gravitational waves, all of them from binary system. So what we do actually, we calculate the amplitude of this actually 6 mode. Like what I said, the HB always proportional HR, but we find the vector mode is extremely low because of the constraints from sigma answer from gravitational wave. So we just plot this 4 mode. You can see here actually we have the theta, the angle theta. One is actually the dotted line is Einstein ether. The solid line is actually Einstein theory. So actually from this figure, you can see more clearly with the actual frequency. The frequency you can see actually if we can really observe the frequency of binaries like space detectors, so we can actually also distinguish actually Einstein ether theory. The reason why, because you see the frequency in Einstein ether theory is much higher than Einstein theory, because here we have actually 2 additional radiation channels, the monopole and the dipole, or the spin 0 graviton and the spin 1 graviton. In Einstein theory, we have only 1 channel for radiation, which is the spin 2. So you can also see the difference of amplitude, A plus and A cross. So which means actually, if we do like what we expect, the gravitational wave can be observed. Yeah, hello? Yeah.
And we'll finish in a few minutes.
Okay. Yeah, I will be finished actually within 5 minutes. Okay. So this shows what's the difference of gravitational wave before they are merged in the inspiral phase. As we expect, the space based detectors will observe such gravitational waves. So we actually think this is a very promising direction we can test Einstein ether theory. Of course, we also calculated the phase difference and the amplitude difference of gravitational waves. So this actually looks likely because actually there's a lot of effect. So we just actually show you once we get this actually difference effect, we can compare the theory with observations. So we just calculate all the PPE parameters. So it's ready to really fit with observations once we observe gravitational waves emitted from inspiral phase. So yeah, this actually I'll quickly summarize the result. So we numerically first find spherical black hole solutions. which are the only ones that satisfy all the current observation conditions. Then, from the considerations of strong field regime, like GW 1708-17, we find C1 is almost a zero. Actually, it has to be less than 10 to minus 15. So when we consider stability of this black holes, we find C4 has to be zero. So then you can see the four-dimensional phase space now reduced two-dimensional. We also actually generate the PPE formula because so far the PPE formula only certifies the without spin 0, spin 2 mode. So we have to generate this, then get the phase space and also amplitude. So once we observe such a gravitational wave, we can fit the theory with observation. So we also apply our general theory to the three-body system. We found actually the dipole is the effect of a dipole is important. So using this kind of gravitational wave, we can also further constrain the theory. So I just quickly outlook. Now we just calculated the post-Newtonian approximation, the PPEs to the first order. We needed to go to second order to actually to use this to test the theory. We also needed to figure out the renown, the Quasinormal mode, which we are working on. Of course, now so far the gravitational wave are all spherical symmetry. We also needed to consider no spherical symmetric gravitational waves. So once we understand this, actually, you can see we can easily generate to other theories with a broken Lorentz symmetry. So I will stop here. Okay. Yeah.
Thank you very much.